For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at https://www.computernetworkassignmenthelp.com. Clustering: consider the Erdős-Rényi random graph G1, N, P with mean degree A. Show that in the limit of large N, the expected number of triangles in the network is a constant. Call delta I, J, K as the indicator random variable that denotes a triangle between I, J, K. Then B. Calculate the clustering coefficient C in the limit of large N. Note: the clustering coefficient is defined as 3 times the number of triangles divided by the number of connected triplets. A connected triplet means 3 vertices with edges U, V, and V, W. The edge U, W can be present or not. Call is the indicator random variable that denotes a triple between I, J, K. Clustering coefficient equals P. computernetworkassignmenthelp.com. Lim infinity P equals 0. C. Calculate the clustering coefficient C for the Erdős-Rényi random graph G2, N, P with P, N equals a log N/N. Compare your answer with part B in the limit of large N. As shown before, it is just P and still 0. But since P is larger in the latter case, there is a higher chance that a triple is actually a triangle. D. 2 points. Compare the ratio of the diameters of G1 and G2 in the limit of large N. For the value of P in G1, the graph is almost surely disconnected. As a result, it has infinite diameter. On the other hand, G2 has a diameter that is omega log N and is almost surely connected. Therefore, the ratio G2/G1 equals 0. E. Now, consider a different construction for a random graph model. We take n vertices and go through each distinct trio of 3 vertices and with independent probability P equals connect the trio using 3 edges to form a triangle. Compute the mean vertex degree and clustering coefficient for this network model. Pick an arbitrary vertex I. Let ij be the indicator random variable denoting a link between I and j. Then computernetworkassignmenthelp.com. Then the average degree is E, ij, n1 equals A. Observe that in this case the number of triangles grow linearly as the number of nodes. Number of triangle equals also the number of triples of occurs when either of is a triangle or there are triangles of J and VWK and no triangle of where J, K equals 6U, VW. Call the event of no triangle in of, but there exists a triple between them as. The ratio is roughly 3/3a plus 1, and points have been awarded to show that the clustering coefficient is a constant, does not decay to 0 as n infinity. 2. Centrality in infinite graphs. computernetworkassignmenthelp.com. In this problem, you will demonstrate an example that shows that eigenvector centrality can be very sensitive to minimal changes in a network. The problem is broken into different components that finally lead to the conclusion. Part 1 first, consider the infinite ring network as in Figure 1. Assume that 11 is the eigenvector centrality measure of node I. A. Show that the she's are computed by finding the largest lambda for which there exists a set of 11 for I equals 0, 1, 2, such that computernetworkassignmenthelp.com. I equals 11-1 plus 11 plus 1, for all I equals 1, 2. Note that we can always normalize the eigenvector centrality by dividing 11 by x0 for all I, so that x0 equals 1. This follows by representing the ring network as x equals lambda x, where lambda is the largest eigenvalue and A is the adjacency matrix. B. Show that all the nodes have equal ranking. Hint. Show that these 11 equals 1 for all I. This should be a straightforward conclusion and can be proved by inspection. One can argue by symmetry or show that lambda equals 2. If lambda equals 2, all 11 equals 1 is a solution and hence the eigenvector. Lambda cannot be larger than 2. If so, and xt was the largest, then lambda xt equals xt1 plus xt plus 1 less than or equal to 2xt. Lambda less than or equal to 2 indeed. Part 2. Next, as shown in Figure 2, we add an edge between two nodes so that the infinite ring is divided into two symmetric halves. We will examine the eigenvector centrality of this new network. By symmetry, we only need to find the eigenvector centrality. Computer Network Assignment Help.com. Figure 2 measures indexed by x0, x1, x2. As before, we always normalize it so that x0 equals 1. C. Write down the system of equations which characterize the eigenvalue centrality. Lambda x0 is equal to 2 times 1 plus x0. Lambda xt equals xt1 plus xt plus 1t greater than 0. D. Show that the eigenvector centrality must satisfy x0 greater than or equal to x1 greater than or equal to x2 greater than or equal to 0. Hint. Start with an initial guess 11 equals 1 for all I, and try to iteratively compute the eigenvector. You can prove the inequalities by induction. Take initial guess as 11t equals 1, where Computer Network Assignment Help.com. Clearly for t equals 0 this is true. After many iterations this will converge to the true centrality. Assume this for t equals k. Now observe 4. The last inequality follows from inductive hypothesis. E. Show that the largest eigenvalue lambda must satisfy 2 less than or equal to lambda less than or equal to 3. Hint. Observe the system of equations you wrote down for C. Lambda greater than or equal to 2, because if we sum up the equation in C, we get. Since x0 is the largest, we also have that lambda x0 is equal to 2 times 1 plus x0 less than or equal to 3x0. Computer Network Assignment Help.com. F. We have shown in part E that xn is positive and decreasing in n. Please prove that lim infinity xn equals 0. Hint. Consider writing the system of equations in Q2 into the form of a linear dynamical system with state y, n, given by. Write down the recursive equation y, n plus 1, equals I, n, that describes the evolution of the linear dynamics, and think about the equilibrium. Now you have demonstrated that by adding a single edge 1 can change the relative centrality measure drastically. Observe that for all n greater than or equal to 1. Then since xn less than or equal to xn1, we only need to show that there is an eigenvalue of A that is 1. As it turns out, that eigenvalue is Computer Network Assignment Help.com. It can be shown that lambda 1 whenever lambda 2. This implies that xn 0. 3. Synchronization. An oscillator is a simple dynamical system that can be modeled by a first-order differential equation. A network of n oscillators can be modeled by a system of differential equations of the form where theta I represents the phase angle and is the state of the oscillator on vertex I, omega is a constant.